pretend that all these features were conditionally independent of each other given the label. Now let's kind of think about this. Let's say you have two features like temperature and wind. I'm not going to write all of these again, so let's just call it P and W. So I need to decide whether to play tennis or not, and we were trying to the argument from the last lecture said that what we need is a probability of P and W conditioned on whether I should play tennis or not. But the naive Bayes assumption says, yeah, sure, maybe the temperature and wind random variables interact with each other in real life, but I'm going to pretend that knowing whether I'm playing tennis or not is going to completely make these things independent, and I'm going to pretend that this is equal to P of T given play times P of W given play. So I'm going to pretend that all these features are conditionally independent of each other given the label. And then let's see where it goes. So more generally, instead of thinking of just two features, if you have B features, you're going to say that the probability of the x1, x2, all the way through xd conditioned on y is simply the product of all probability of xi's given y. Originally, we had, if I have to enumerate all d things, all possible combinations, you needed 2 power d numbers. Now, this one is 2 numbers, this one's 2, this one's 2. There are just d numbers. So this really, and this is a probability, right? If you had booleans, if this is a probability, it can either this could be something like 0.1, 0.9 for x1 is say, just write this up more clearly. So this could be say 0.1 and 0.9 for x1 being 0 and 1, for x2 being 0 and 1, the probability could have been minus 5 and so on. Notice that the value for x1 is completely not depending on x2, so you just have d possible numbers, not even 2d, because if I know this one, I can calculate this. So just d numbers. So in the original the original setting where we had no assumptions, we needed an exponential set of parameters in our model. Now we only have a number of parameters that's just linear in the dimensionality. That seems like an improvement. What's wrong with having an exponential number of parameters? No, seriously, what's wrong? Well, can you give me a technical argument for why that's a problem? And actually, there are 2 possible answers here, and can someone come up with maybe one or both of these? Yeah, Boston.
One reason would be that you have to assume a simple model to be able to handle this small number of features, so that it doesn't become unmanageable.
Which one are you talking about? The one on top or the bottom?
Just in general, having exponential.
Number of parameters is, so can you repeat that?
Yeah, just that you have to, you may end up having to assume a simple model to do it.
Essentially it kind of flies in the face of this whole philosophy that simplicity is better. Right? Exponential number of features is a level of complexity that we don't want to handle. It goes against Occam's razor. Yeah?
I also think since there's exponential amounts have to share 1, like they have to add up to 1.
Yes.
The probabilities, each one of those singular probabilities will be very low.
Okay, so that's a valid point, but is that really a problem? Small numbers, we can handle it. Our computers are mature enough that we can handle small numbers, and worst case we can store log probabilities. Log probabilities are not going to be small numbers. But hidden in that, you had another hint of another answer, which is if you have an exponential number of features, an exponential number of parameters, each one of those is going to be hard to estimate because they might essentially become too either small, you might run into numeric issues when you are estimating them, or more generally, to kind of run with that argument, how much data do you need to estimate this exponential number of parameters? If you have an exponential number of parameters to train, we will need roughly an exponential number of amount of data to train it. So we are not going to have enough data to fit that model, and that's really, it follows from this Occam's razor sort of an argument as well. Of course, there's also the other sort of simple argument against exponential number of parameters.
You're saving time and memory.
Yeah, exactly. I don't have an exponential amount of time to make one prediction. So there's really just no reason to do that. So on the other hand, what we're going to do is, complexity is bad, so let's make a simplifying assumption. That's really the philosophy here. Complexity is bad, we're going to make a simplifying assumption. The way we make the simplifying assumption that naive Bayes makes is that features are independent of each other. And features are conditionally independent of each other. So they are not independent of each other, they are conditionally independent of each other. And this is a common mistake that people make. We are not assuming that the features are independent of each other unconditionally. The features are independent of each other conditioned on the label. So what that means is, it is not true that P of x1, let's say we have 3 features, it's not true we are assuming that P of x1, x2 and x3 is equal to, this is completely not the case. What we are assuming is the probability of x1, x2, x3 conditioned on y is the product of the probabilities of xi conditioned on y. Unconditionally, we are not making any assumptions. There is no assumption in this, anything that we have done, that the features are independent of each other. The features are independent of each other, conditioned on knowing the value of y. And this is important. This is a common mistake that people make, and I just wanted to highlight that. More generally, at this point, we need to make a prediction. What do we need? We need the priors and the likelihoods. The priors, we made no assumptions about the priors. The priors is just P of y. It's kind of, if you have 2 labels, it's just one number. If you have k labels, it's k minus 1 numbers. Not a big deal. So we need the prior, and we need the likelihood. The likelihood, we needed P of y, x given y, but now we have this way of constructing the likelihood term using this assumption. So we need all these class conditional, it's also called class conditional likelihoods or label conditional likelihoods. We need these likelihoods of each feature conditioned on y. At the decision rule, let's just to wrap this up, the decision rule for naive Bayes was, we are doing maximum a posteriori estimation. We want to find the label that maximizes the value of the posterior probability, which is the same as the label that maximizes the product of the likelihood and the prior. But now we have made this naive Bayes assumption that the likelihood is just the product of all these things. So you need to maximize, you need to find the label that maximizes this product, the product of the prior times, just multiply all these feature probabilities conditioned on the label. Before we move on, are there questions about naive Bayes? The naive Bayes assumption. Yes?
So on the slide where you were saying something about exponential,
Yes.
I didn't see why we're talking about exponential.
Oh, it's this one here?
Yeah.
So think about it this way. So the question was, why are there exponential number of parameters? So forget the prior. The prior is simple. So this is probability of y. Let's say we have k labels, then you just need probability of y equals 1, probability of y equals 2, and so on. K things. Now the likelihood is a term that looks like this. It's a table, really. It's a table that, let's zoom in. So you have x, you can have d features, so feature x1, x2, all the way to xd.
Let me rephrase my
Yes.
So I thought you were saying the exponential had to do with after you get the condition.
Yeah, even with the conditional probabilities, right?
Okay.
So I'm going to say what's the probability of x. So it's probability of x given, let's say y equals 1. The conditional probability. So probability of x given y equals 1 is really a function that takes a particular value of x and assigns a probability to it. It can take any value of x and assign a probability to it. It needs to. Which means x can be all zeros. You need a number. Let's say some number here, p of x condition on y. It can be all 1. All these things. So every possible entry in this truth table needs a certain value. How many rows are in this truth table? So every feature can take 2 values, and they are all independent of each other, so it is 2 power d. So this table has an exponential number of rows, which means you need this, every row here corresponds to a certain number, so you need an exponential number of parameters for y equals 1. You need a completely different table for p of x conditioned on y equals 0. So you need twice the number of things. If you have k labels, you have k times the number of things. So you have an exponential number of parameters. Other questions? Yeah?
Sorry, why do you have a minus 1 super?
Oh, good. So that's just, I put that there so that I get a question. See, this table is showing a probability, the table that I drew. We know that the entries of that table have to add up to 1, right? Which means I have the luxury of not remembering the last one, because it's just 1 minus the sum of everything else. So I can, I get this one memory slot that I don't need to remember. And someone pointed to me after class that, yeah, but in order to compute that, you need to add an exponential number of things and do 1 minus that. So that just seems stupid. Which is true, but technically this is correct. Technically this is correct, and we will actually use, in the naive Bayes case, actually it will end up making sense. Here, it's just you don't need to remember, you have the luxury of not remembering one thing. So this is the fewest number of parameters needed. Does that make sense? Other questions? Yes?
So, can we view dependence as, I'm trying to understand the naive assumption.
Yes.
Can you view dependence as like a measure of correlation?
It is exactly a measure of correlation.
So then, are we, in our naive assumption, are we assuming that all correlation between the features was caused by those features correlating with the label, and that there was no other like correlation?
That's exactly right. The naive Bayes assumption is naive in the sense that it assumes the features are completely uncorrelated with each other if you knew the label. And if you put it that way, that doesn't seem like a right thing. How could it possibly be that temperature and wind are uncorrelated with each other depending on whether I decide to play tennis or not? Right? It seems totally made up, and as I'll mention later, yet naive Bayes kind of works. It's one of these mystifying things that it kind of works reasonably well. It's a surprisingly better than baseline classifier. That's a very low bar, by the way. Better than baseline is not a big bar, but it's even that fact that it does anything is not is surprising. And there are various explanations for these. If you are interested in talking about why it's possible that naive Bayes works, come talk to me afterwards, and I can point you to some interesting papers that talk about what kinds of distributions these things characterize. But yes, that's right. The naive Bayes assumption essentially is saying that in using the naive Bayes assumption, you would be assuming the following. You would be assuming that if knowing the value of the label, all the features are completely independent of each other, completely uncorrelated with each other, and do not affect each other. Knowing the value of the label. And perhaps that's not a great assumption, but we'll see where that takes us. This is what I mentioned, whenever we have an intractable problem, we have 2 ways of going ahead. we just brute force our way through and pretend that we can solve it and hope it works, or we make assumptions that invariably end up giving up quality, meaning we don't have the right distribution anymore, but it ends up also, computationally feasible. So you approximate it and hope it works. Hope it's good enough. You come here for machine learning, you get life lessons. But okay, so the decision rule of naive Bayes is really this: find the label that maximizes this value. One interesting question that we could think about is: imagine you have D features. Before we came to the Bayesian worldview, we had these D features. These were points in the D-dimensional space, and we talked about linear classifiers and nonlinear classifiers, and we talked about hyperplanes, that slice the space. We still have D features. This is still a function. This, the h and b is still just a function. It takes a point in the space and assigns a label. So maybe, in two-dimensional space, it takes a certain point and maybe it makes it a plus. It takes another point, it makes it a minus, maybe it takes a point and makes it a plus. And there is a certain, region where both the pluses and where it's completely equal. Maybe the plus and the minus are equally probable. This is the decision boundary. For perceptron, for SVM and all these things that we saw before, the decision boundary was linear. We were looking at linear classifiers. One interesting question is, what is the decision boundary between the pluses and the minuses according to this particular decision rule? And in order to derive that, we could ask, at what point when does this particular classifier assign a label plus to an example? So when would it assign a label plus? It would assign the label. So let's just let me write down the thing. So label is plus if the probability of plus given x is greater than the probability of minus given x. Right? You find the most probable label, which means you find if the classifier predicts a plus, it means that the pluses get a higher probability. But we also know that the posterior probability is just the product of the likelihood and the prior, blah blah blah. So the label is plus if this quantity is more than this other quantity. Before I start manipulating this, are there questions about this? Notice that inside this, the naive Bayes assumption is sitting right here. That's the likelihood term. In both cases, those are the likelihoods. Right? Okay, there are no questions. The label is plus if the probability of plus is greater than the probability of minus. I can just reorganize this, right? I took the negative side, I took all of this and brought it down to the denominator, and let's pretend that we live in a world where we don't have any zeros. So this is a valid operation. So if the label is plus, if this ratio is positive, right? I could now take log of this. So if the log of this quantity is greater than equal to, let's make it greater than equal to 0. Log of 1 is 0. Right? The label is plus if the log of that quantity is greater than 0. Now I'm not going to prove this, but I think there's a note on the class website which actually walks you through the proof. But if you take this log of this quantity and just work it through and simplify it, it ends up being that the label is plus if a certain value of weights dot the features plus a bias is greater than 0. This is kind of a weird thing. We start off with naive Bayes assumptions and features being independent and all that good stuff, and it turns out that the decision boundary is linear. It's actually a fun proof. I mean, this nice little manipulation that works, and I encourage you to take a look at it. It turns out that the naive Bayes, it could have done anything. There's no reason for it to have put a linear decision boundary. it could have, if you have pluses and maybe you have minuses here, it could have done something like all of this is plus. There's nothing that prevented that from happening. It just so happened that the naive Bayes classifier is also a linear classifier. Okay, now the important point that I would like to kind of emphasize here is, yes, the naive Bayes classifier is a linear function in the feature space, but it turns out that not every linear classifier is a naive Bayes classifier. So the set of naive Bayes classifiers is a strict subset of all linear classifiers. And this will become an important point when we move to logistic regression. It's just something that I'll mention again, but I just wanted to seed that idea. Yes?
What does this mean?
What does which mean?
In like words?
In
If you wanted to say it in words.
which one?
The log of
Ah.
the negative one.
So it just means that the ratio of these, the what do you call it, the negatives, the posterior probability of the negative to the positive is a linear function. And if this ratio is greater than 0, that means this classifier would have chosen the label to be, oh, I put a minus on top. If the ratio is great, let's say less than 0. If the ratio was less than 0, the classifier would have chosen the label to be positive. That's equivalent to saying if W transpose X plus B for a particular choice of W and B is less than 0, the same classifier would have chosen the label to be positive. What that really means is the boundary between when the label is positive and negative in the feature space is a linear surface. So, in other words, the naive Bayes classifier, the decision boundary of the naive Bayes classifier corresponds to a particular hyperplane. Some hyperplane. You've been learning hyperplanes with perceptrons and SVMs and all that. Turns out this one is also finding some hyperplane in choosing these particular features and the likelihoods and the priors. It's choosing a particular hyperplane. The construction, the proof, actually gives it's a constructive proof that shows which hyperplane gets chosen. Other questions?
Does that mean, like, if we have a data set that is not linearly separable, this won't perform that well?
Oh yeah, that's a good observation. If your data set is not linearly separable, the naive Bayes may not perform well. That's a good point, but let's take that and run with that a bit. If the same is true for perceptron, the same is true for SVM, did that prevent you from using an SVM in your project or a perceptron in your project? No. There is real life, which has all its complexities, and there is your model of real life, which you can compute. The model is not a perfect mirror of life, but it gives a reasonable performance. So this is always true. All models are wrong. Some models are convenient. Did you have a question? No. Other questions? Yeah.
So maybe it'll get to this, but then, like with SVM, we could kind of adjust the margin, like, to make it like if our data isn't linear separable, we could.
You could mess around with it. You can directly learn the hyperplane to make it work.
Yeah.
If you take that exact intuition and run with it, you get logistic regression. Yeah, it's kind of disappointing, as we see when we all the low hanging. If you can think of an idea in 30 seconds, somebody else probably thought of it, which is a very disappointing fact. But if you get to the edge of what we know, those 30 seconds might get you something big. But yes, that's a good point. All right. So what we spoke about now is what is the naive Bayes classifier. What you need to know is what a naive Bayes classifier is. It is at the heart of it. It's basically a function that assigns probabilities to labels given examples. And it's not any function. It's a particular independence assumption. Naive Bayes is used only for that particular independence assumption, which is that all your features are conditionally independent given the label. That's the naive Bayes assumption. What you need to know is what the naive Bayes classifier is. You need to know what the naive Bayes assumption is. You need to know what the decision boundary of the naive Bayes classifier is. And maybe in one of your homeworks, actually there's going to be only one more homework, which probably will be out sometime today or tomorrow. You will be able to, you might be able to, you might have to prove that it's linear for some class of functions. So we've not spoken about anything about learning these things. We only talked about what these things represent. So anytime you see a new hypothesis space, you must, in your mind, go through your checklist. What does this represent? What are we actually learning? How do we learn these things? And how do we make predictions with this hypothesis space? Right now we have covered what it represents. We have covered how to make predictions. The only thing left is how do we learn? And of course, we need to eventually deal with practical issues like actually implementing these things. We'll get there later. So, in order to learn the naive Bayes classifier, let's kind of think about what the hypothesis consists of. In this case, your hypothesis, your function that completely characterizes the classifier is just a collection of these probabilities. If you have some methodology to get me both the priors and the likelihoods, you've given me the classifier. So the job of the learning algorithm is to somehow produce, using data, a value of priors. I mean, not but depending on the number of labels. This might be the easiest classifier to extend to multi-class. So, but I'm going to pretend that we are only talking about binary. So, you need to give me a value of the probability of y given plus. You need to give me probability of x given y equals plus. You need to give me the value of probability of x given y equals minus. All these numbers together give me the classifier. Because once you give me these things, I can produce the, I have the decision rule. Like all cases with learning, we assume that we are given a data set. Let's assume that we are still in the supervised setting, so we have a data set consisting of examples, xi's, with, that are paired with labels, yi's, that were generated by an oracle. And let's say we have many, many examples of this kind, m examples. Now, I have to warn you, the next maybe 5 slides are going to be just a big mess of notation. You'll have, I'm going to have something that I hate, namely, which is 2 subscripts for every variable. And it's going to get messy. I promise you it's easy, but ugly. So what I encourage is you should go home and work out the math yourself. It's really easy math, but just so painful to actually write. Yeah?
Before going to the math, I have a question. Yeah, it says likelihood for a feature given the label.
Yes.
So it's like for every label, there's a set of xj, right?
Yep.
And
Yep.
if
So
you go back to 3 slides.
3 slides. 1, 2, 3.
And another one. Yeah, this equation. On the right side, W transpose
Yes.
x, and this x, which x is
It's a vector. It's the entire vector.
Yeah, it's conditional.
So this is really sum over j, wj, xj.
And this x is conditionally given.
No, this is, we have no conditioning or anything. X is just the feature. It's the value of the feature. On the right side, we have probabilities. To my right, to your left, you have probabilities. On this side, you just have features and weights. There are no probabilities anymore.
Oh, so this x is
It's just literally the same x's that you had so far in your homeworks and
okay.
all the other examples that we saw.
So that's the values of the feature.
It's the value of the
It's
feature.
not a okay.
It's not the probability. Yes. Yeah. There's no probabilities on the other side. Okay, so as I was giving you dire warnings about ugly notation, I even wrote it down. So the convention that we're going to follow is we're going to use I to index over examples in the data set, and we're going to use j to index over features for each example. And now that I write it this way, my i's and j's look the same, so I should probably use i's and k's. But anyway, so the ith example is xi and yi. The jth feature of the example xi is xij. Okay? Just to keep that in mind, I is an index over examples, j is an index over features, and for every example, xi is a vector. This is roughly the convention we've had so far, but I've never explicitly written it as indexed over the features. We will need to do that for this particular classifier. So we need to, okay, before we get into the notation, what we have is we've been talking about the naive Bayes classifier. The naive Bayes classifier uses map prediction. We're going to use a probabilistic criterion for choosing the hypothesis. We need to find the best hypothesis. How do we decide what is best if you are Bayesian? What criterion of what learning criterion could you use? Yeah?
Most probable.
The most probable, but if you want to be fancy, you could call it MAP. Maximum a posteriori learning. Or, if you want to be somewhat simpler than that, you could use maximum likelihood learning. So, if you are Bayesian, the probabilistic criterion to select hypotheses is either maximum likelihood or maximum a posteriori estimation. MAP learning or MLE. I'm going to work through the details of maximum likelihood estimation simply because the math is a little bit easier. The maximum, just to remind you, we are now, when we are doing maximum likelihood estimation, we are being Bayesian about the criterion for choosing a classifier. In this case, the classifier is this set of probabilities. So, the classifier that this criterion decides to use is the one that is most probable, the most likely given the data. In other words, we are going to find the classifier that maximizes the likelihood of the data given the hypothesis. Here H, the hypothesis is defined, is just a collection of all the probabilities. So we want to find the classifier. Now, this could get a little bit tricky. So there are two kinds of probabilities we are dealing with. There is the probability that we have a label for a particular example, and then the likelihood is the probability that this data set could have been generated using H, where H itself consists of probabilities. Okay? So just, you might have to juggle a few things in your head, but as long as you are clear that H is a hypothesis that consists of probabilities, and we are going to construct the likelihood of the data, things should be okay. So our goal is to maximize the likelihood of the data, but the likelihood of the data is just the product of all the likelihoods of each example, right? So we want probability of the data given the hypothesis, but that's just this quantity here. The data consists of all these pairs, and we have from the start made the assumption that all examples are independent of each other, so we can basically decompose P of D given H into this big product of over each example. Okay, so we can represent P of D given H as this product. Now, the thing in the box there, really P of xy given H, is asking what's the probability that a particular classifier would assign to this pair xy. Now, why is this interesting? Because our classifier itself, our classifier is basically just a box that assigns probabilities to examples. So we can actually, the naive Bayes assumption is going to help us there. So we want to know what's P of x comma y given the hypothesis, where this is really all the numbers that were in those tables. You remember those big tables for the tennis example? All the numbers in the table is contained inside H. If you have that table, you can calculate the probability. So that's really what we are doing here. So it's really P of xy given H, but now we know that P of xy given H is really P of y given H times P of x conditioned on y. This is just standard rules of probability. There must be really nothing that is alarming about this. Okay?
So
Good. Yeah?
any H.
Any H, that's right. we don't know what the h is because we are trying to maximize all these things. So we need to think about it as in terms of the function. So the way to think about h is at this point, h is really a box that contains the prior, which is really p of y up front, and the likelihood, which is really p of xj conditioned on y, and p of y equals plus, and p of xj conditioned on y equals minus for every j, for every feature j. So every hypothesis is going to contain all these numbers, and our goal is to compute those two probabilities using these terms. And the reason we have these p of xj's and not entire x is because we already made the naive Bayes assumption, but that's what I'm going to formalize next. P of x and y given x is simply the product over all j's of p of xj conditioned on y and h. H is just the classifier that we have, and this has gone here, right? So this is where the subscripts kind of get a little bit hairy. But what we have, this is the instantiation of the naive Bayes assumption. We needed the likelihood of the example, that's the box on top. But the likelihood of the example conditioned on the label is simply the product of every feature. Question? Yes?
Are those being multiplied together, or is
Sorry, are those what?
being multiplied together, or is one contained in the other?
They are multiplied together. So I don't understand the question. So I'm going to put a set of brackets to help you out.
Yeah.
This goes this way. Is that?
Okay. That's not. Yeah. That's.
Because multiplication is, yeah, it's nested. And one way of seeing that it's nested is, see, there's an I here, there's an I here, there's a J here, there's a J here. So it is nested. So this whole thing is this bracket here, and this thing here is this thing. So we just track the probability of one example. Okay? Okay, so far we have made two assumptions to start off with. The first assumption was that every example is independent. That's what gave us this probability, this multiplication, and then we assumed we had the naive Bayes assumption that gave us a way to simplify the likelihood. Okay, now what do? I need a way to maximize this large product. How do you maximize products? Someone mutters an answer but is not brave enough to say it. Take the log. We've been doing this all the time. You see a large product and if you want to maximize or minimize, your instinctive reaction is, let me take a log and see what happens. Chances are your life will get better. You take little victories. So you take the log, all the products became summations. So we had, and at this point the nesting becomes very clear because I just separated out, I took this, this product in. So we have, this becomes a log prior, and then this becomes a log likelihood. And we are summing over all the examples in both cases, and inside, for the likelihood, we are summing over all the features. This is just a mechanical operation that you should be able to do. And technically this is correct because log is a monotone function. So, you're not violating any cardinal laws here. Okay, so we need to maximize the log likelihood in order to get the maximum likelihood thing. We have this large summation here. What could we possibly do now? We need to maximize this expression. Can you solve this now? So we have everything we need. Or let me ask you another question. I'll tell you we don't have everything. What's missing? I'll encourage you to think of your project, for example, or one of your homework questions. What do you need to make this work? Yeah?
What if your x's aren't binary?
What if your x's aren't binary?
Like in our example, like our
In the project?
yeah, the project.
Right. You need some way of, more generally, p of xj given y and p of yi or y, so p of y, this quantity here and this quantity here is just a function. We don't know what function it is. It could be any function. At this point, we can't solve it without actually making an assumption about what that function actually looks like, right? If it is binary, that function might be different. If it is integers, that function might be different. If it is real values, that function might be different. We need to make an assumption about what that probability actually is. And this is the modeling assumption. Finally, we come to a point where we start making modeling assumptions. We need to actually make an assumption about what those probabilities actually look like, because we don't know what functions they are. If it's an integer, maybe certain choices are easy. If it's real numbers, maybe some other choices are easy. What I'm going to do now is I'm not going to talk about the general case. The general case requires you to make a functional assumption, and every functional form that you assume gives you a different naive Bayes classifier. I will work through one particular case where all your features are Boolean or binary, and I'll hint as to what the general case would be, and maybe in your homework you will do one more case so that you can get a hand for it. What we'll assume is that, let's assume that, let's assume that all the i's can be either 0 or 1. That's easy because that's just a binary classification. That's not a new assumption. We'll also assume that xij is also 0 or 1. So we have only binary features. These are indicators like, does the word pancake appear in an email, true or false, for a spam detector? I'm not saying that I get a lot of pancake spam, but maybe it's correlated with not pancakes, not spam. Okay, so what we have here is an assumption that all our features are binary, which means we can actually, we can start actually enumerating these probabilities and putting symbols to them. So let's assume that because the features can be binary, we can say that the prior distribution is just a coin toss. The probability that, let's just give it a name, the probability of y equals 1, let's call it p. The probability of y equals 0 is just 1 minus p. This is the functional form. This is the function. This function is defined by this number p, which means if I know the value of p, I get that probability. Likelihoods are going to get a little bit more ugly. The probability that a feature xj takes the value 1 when the value of the label is 1, let's call that aj. So aj is just a name for this property. This is the simplest function that I can think of. It's just a constant. Probability of xj equals 1 given yj equals 1 is aj. Probability of xj is 0 given yj is 1 is 1 minus that, because those two probabilities have to add up. Now this is when y equals 1. This is when the label is positive, or the class is true. When the class is false, we have a completely different set of parameters, because these are two separate probabilities that we have. This is like in the table we had the top part of the table when playing tennis was yes, the bottom part when playing tennis was no. When when the value of y is 0, the probability of xj equals 1, let's say that's bj. And when when yj is 0, the probability that xj is 0 is 1 minus bj. Now, this is where I said, we are going to have a ton of notation. There is no hope that you're going to remember all of this just having seen it once, which means you have to go home and work it out. But I'll keep reminding you what these symbols mean. So we have made this assumption that our features are Boolean. As a result, we can say that all our probability distributions are basically like coin tosses. So the prior is completely characterized by this one number p. The likelihood consists of two sets of numbers, the a's and the b's. A's correspond to A is a vector, right? It's like a collection of one for each feature. A corresponds to the likelihood of the jth feature being 1, conditioned on the label being true. B corresponds to the probability that the jth feature is 1 when the label is false. The hypothesis, H, is really a big box containing the likelihood and the priors, so it contains all the A's, the B's, and the value P. So if you give me an assignment to all the A's, if you give me an assignment to all the B's, and if you give me the value of P, what you have given me is the naive Bayes classifier for the case when there are two labels and all features are binary. So the job of learning now is to determine what the values of A, B, and P are. So our goal of learning is to find what these parameters are. Right? Before I introduce one more kind of annoying notational detail, are there questions? Yeah?
So if we were going to expand this to multi-class, we would just need more labels, more priors, and more tables.
You would need, here there are two classes, so there are two rows here. So you would need, if you had three classes, you would have one more. And you would have one more term here.
Okay.
Yeah. That's why naive Bayes is kind of really easy to extend to multi-class. Turns out everything is easy to extend to multi-class, but this one does not take the least amount of work. Okay. Let's now, job of learning is to learn the priors and the likelihoods. So let's learn the prior first. Let's focus on the prior first. Now, what I need is to write down P of y given h in terms of this number P, right? So I want to write P of y given h. It's really what? It's equal to P when y equals 1, equal to 1 minus P when y equals 0. That's really what I have written, exactly the same thing here. Now, instead of writing it in this sort of a multi-case sort of definition, what I could do is I'm going to introduce a bit of notation that actually is going to make the calculus a little easier instead of writing it this way. Suppose I introduce a certain gate, a flag that says P of y equals h is P if I'll write down what's in those boxes. This is saying this is 1 if y equals 1, 0 if y equals 0. This is 1 if y equals 0 and 0. Would you agree that the thing at the bottom, if I was able to construct something like this, the thing at the bottom is the same as the thing at the top? Because when y equals 0, only this term will survive, and so you get 1 minus p. When y equals 1, only this term will survive, and you will get y equals, you'll get the right thing. Right? Those things in those boxes are called indicators. An indicator is just this device that looks at a certain Boolean, like this is really a condition, right? It's an indicator for a condition. It indicates what I've just let me, instead of pointing to the slide, this thing here is an indicator for the condition that y equals 1. This thing here is an indicator for the condition that y equals 0. I can give it a name. I can give it a note. I can, instead of drawing boxes, because boxes don't look very respectable when you typeset things, we're going to give it a notation. But you have a question?
Probability of y equals h.
Oh, that's completely wrong. Thanks. That makes no sense. Probability of y equals 1. Probability of y. It's just probability of y. And if you want, it's probability of y given h. Yes, thanks. First, before getting into these details, would you agree that the case definition is the same as this if I was able to fill in these boxes correctly, if I had some way of constructing these boxes?
Yes.
Yes. let's give those boxes a name. They are called indicators. Indicators exist in computer science all over the place, and you have used it whether you may realize it or not. Some people call it the Iverson bracket or anything you want. Instead of putting boxes, I'm going to just put square brackets. This square bracket z is called the indicator function. It is equal to 1 if z equals true. It's equal to 0 if z is false. Think of it as a gate. Instead of adding things this way, what I have done is slightly different. I'm going to multiply them by saying probability of y given h is equal to p power indicator for y equals 1 times 1 minus p power indicator for y equals 0. Now, only one of those conditions are going to be true, which means when yi is 0, the probability of y becomes 1 minus p. When y equals 1, the probability of y becomes p. So it's exactly the same. This is a compact and convenient way of writing exactly the same. It turns out this is compact and convenient, and it's going to help us with the math quite a bit, and so that's the reason why this shows up. Questions about the indicators? Because I'm going to actually now show you how to write the likelihoods using indicators, and I promise you it's ugly. So before we move to that, let's get to this. There are no questions. Let's go to the yes.
Do you mean those to be exponents?
Yeah, I actually mean those to be exponents. Because anything power 0 becomes is 1. So if let's take the case when y is 0. When y is 0, this quantity becomes 1 and this quantity becomes 0. Which means you get p power 0 times 1 minus p power 1, which is exactly 1 minus p. It's a really convenient mathematical trick to write down these cases in terms of indicators. Of course, you have to live with the fact that sometimes things you have to write a lot. I can write the likelihood as something like this. So the likelihood consists of these two rows, right? There are 4 possible values that the likelihood can take. When y is 1 and x is 1, the likelihood is 8. When y is 1 and x is 0, when y is 1 and x is 0, the value is 1 minus 8. So you have 4 cases. Every case becomes an indicator. And you just multiply all these things. You put the indicator in the power and you put the corresponding probability at the bottom. And I'm not going to go through the details. I want you to convince yourself afterwards that these two things, the thing in the box is identical to this thing here. And work out some examples with this, because this is just one of these things where you have to enumerate a lot of things. Okay, the reason for these indicators is now I can actually plug in both these things as single big products. So let me actually work through the details a little bit. So what we had is probability of x, y conditioned on h is, or let me write down the log. Log probability of x and y conditioned on h is log prior probability of y conditioned on h plus the sum over each feature probability of xj conditioned on, oh sorry, not probability, log y and h. Now I'm going to just show you how the indicator gets simplified, how the prior gets simplified. P of y given h based on what we just saw is p power y equals 1 times 1 minus p power the indicator for y equals 0. So the log of this and becomes y, the indicator for y equals 1 times log p plus the indicator for y equals 0 times log 1 minus p. And this is why we are multiplying instead of adding. Because when we multiply and we have a log anyway, you take a log, multiplications become sums. So this is exactly the same as this. Eventually, we are going to take the derivative of these things with respect to p and set those things to 0. If you do that, what you get, you take the derivative and set those things to 0, you get something like this. You get, and I'm actually not working out the details. I want you to work out the details because I don't have the guts to do that and still hope to keep you awake. On the other hand, it's easy, so you should do it. But it's basically calculus 101. It's exactly the same as the simple Bernoulli trials that we saw with those light bulbs. You set it to 0, you set the derivative to 0, you get the value of the prior as something like this. You count how many times the value of y is 1, divided by number of times y is 1 plus number of times y is 0. What is the prior? P is simply the probability of y equals 1. Now, we've gone through all of this notation and we managed to prove that if you have a certain number of 1s and a certain number of 0s, the probability of y is equal to 1 is count the number of 1s divided by count the total number of things. It's a fraction of times it's equal to the y is 1. Just like the Bernoulli case that this is Bernoulli trials. So the maximum likelihood estimate for P is simply derived by counting. Now it's true also for the likelihood and the priors. Aj is the probability. This is the probability of xj equals 1 addition on y equals 1, right? What you do is count how many times xj is 1 when y equals 1, divide that by the number of times y equals 1. This is the maximum likelihood estimate. Again, if you should be able to prove this if you take the derivative of the likelihood term here with all these indicators thrown in and then take the derivative with respect to aj and set it to 0, you should be able to do this. It's a good exercise and you absolutely should do it. Yeah?
So you kind of walked us through the conversion from Bayesian to frequentist, right? Like this is the frequentist approach to statistics where you're just counting the number of total and counting the number of a specific instance?
In this case, these two things end up converging. But in general, if you really want to be Bayesian, and if your heart and soul is Bayesian, you would not be happy with this because you want a probability over, you don't just want the value of P, you want to know what's the probability that P has the value. Now, that looks silly, but you can do that. And you can basically keep putting priors on the way to the outcome, and then you will be a true Bayesian. It's totally doable, and it exists. And if you take that particular kind of approach, you have to think about what are the functional forms of probabilities over probabilities. And if you want a search term to kind of look up, the word is the thing to look up is conjugate priors. Anyway, so you have these things. You get aj is the number of times xj ends up being 1 when y equals 1. Bj is not a surprise. It's the number of times xj is 1 when yj is 0. Right? So what I have done is I have walked through this really complicated process of maximum likelihood estimation, or what looks like a complicated process of maximum likelihood estimation, and come to a conclusion that you could have written down before you saw any of these things. The prior is simply the fraction of examples where the label takes a certain value. The likelihood is simply the fraction of examples that the label takes a certain value for each, a feature takes a certain value for each label. You should absolutely, I'm repeating this multiple times because you should do this, you should go home and work out the details and come back with questions. But before you work out the details, are there any questions?
Professor?
Yeah?
Can you help me understand the difference between the prior we have here and the prior used in maximum likelihood likelihood estimation because my understanding is the difference between map and MLE is that the prior equals 1.
This is a good question. This is a good confusion because here the priors are, in general, if you're in the Bayesian universe, anytime you have, I'm not going to use x and y. I'm going to just use say a and b. Probability of a given b is simply probability of a times p of b divided by p of b. Right? Now, this term here is always called the prior. This term here is always called the likelihood, irrespective of what the a's and b's are. Okay? And let me write this down because you have maximum likelihood estimation where the prior is the probability of a hypothesis taking a value before any data. The likelihood, blah blah blah, is the probability of the data condition of the hypothesis. This is learning. Now, in naive Bayes and in probabilistic models in general, we have the classifier is defined to be probability of x given y times is defined by these two terms. Now, this is really for a particular example. This is not during learning. So this is max. This thing is called the prior probability of a label. This is likelihood of example this is prior probability of the hypothesis, and this is the likelihood of the data conditioned on the hypothesis. The top part is for learning. This is used for maximum likelihood, map prediction. It just so happens, and this is where it gets a little tricky, the hypothesis here, let me use a different color, or let me just highlight. The hypothesis here internally consists of these two things. So we are talking about probabilities of probabilities being certain values. And it's the same criterion that we use to decide which classifier we should pick and what label we should pick. When we are using the criterion for deciding which classifier to pick, you can use maximum a posteriori or maximum likelihood. When we are using the criterion to decide what label to pick, we always use maximum a posteriori. And this is a good confusion, but it's important to resolve. There's only a minute left, and I'm going to set it up without answering the question. I'm going to just give you something to do. I want to work out how to learn a naive Bayes classifier using this tennis data that we saw. And the prior is rather simple. The prior probability of the label is count how many times the label is positive, divide by the total number of examples. So the prior probability is 9/14 for A equals plus and 5/14 for the other class. The likelihood, you need to consider two kinds of likelihoods. You need to go through each case separately, and I'm not going to do that because this is going to, I don't want to stop in the middle of it. So let me stop right now, but I want you to there are two things, exercises for you. One, prove to yourself that I'm not lying, that the naive Bayes estimation that we derived, that I showed you would be the answer, is actually the answer. And two, I want you to actually go through this material and work out the likelihoods and the priors on paper so that you know what it is and you realize how ridiculously simple the naive Bayes learning algorithm is. It's literally counting a lot of things and just doing fractions. So I want you to work out these things and come back with questions. We'll start with this in the next lecture. Oh, and don't forget to go to Kiri's talk tomorrow. It could be fun.